Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm Rosh Shafu, and today's episode is with DC, who's going to show us the contracts behind Worldcoin. DC, thanks for taking the time, man.
Thank you for having me. Uh,
Yeah,
so
wait,
yeah,
I still need to introduce Owen as well. So this is the first time we're doing a co-hosting thing. Owen is a good friend of mine who's really passionate about the ZK stuff. So yeah, Owen, thanks for taking the time as well, dude. Awesome. Then DC, it's your show.
cool. So to start, I think it's always good to give like a bird's eye view of everything that we're going to be talking about today, just so we understand context and sort of what WorldCoin is all about. So as a high-level overview, WorldCoin is a project that's trying to build the largest financial and identity network. And what that means is that we're essentially trying to build a way through which we can prove personhood on the internet and also give our users access to like sovereign in the name of like crypto wallets and all these sorts of things. So the WorldCoin ecosystem is composed of three main components. The top level one, so we can see here, is the WorldCoin token, the WorldCoin app, and World ID. So the World app is a app client for iOS and Android that essentially is a front end for a safe wallet, like a safe smart contract account. And it just gives an easy way for users to interact with the blockchain. The main component of the WorldCoin ecosystem is World ID. So World ID is this privacy-preserving proof of personhood protocol, which we developed using a bunch of tools that essentially allows anyone to prove that they're a unique person in a digital context, whether it's in a smart contract or just as a regular API. So proving personhood just essentially means that whomever who is using your application is a unique person. And we also have this property of Sybil resistance, meaning that a single action by a user, by a user of an app which integrates World ID can only do actions once or a set given amount of times. So for example, if I have a voting protocol and I integrate World ID, I can gatekeep the voting action by World ID and require users to prove their personhood so that they can vote. And when they vote, they can only vote once. And if they vote again, it rejects. And the cool property of this is that the protocol or the app or anyone reading the mempool or the blockchain state does not learn who made that proof, thanks to zero knowledge proofs. So that's a high level overview of sort of what the ecosystem is like. And I want to sort of start with the World ID component a little bit. So World ID was built using a protocol called Semaphore. So semaphore.psc.dev. So it's a protocol built by the Privacy Scaling Explorations Group and the Ethereum Foundation, and it essentially allows you to create privacy-preserving membership inclusion proofs. So imagine you have a set. A set can be just an array of, let's say, public keys, or just like users' addresses, for example. So you can essentially insert entities or public keys into this set, and you're able to prove that you own a private key corresponding to a public key in this set or membership group. And you're able to prove inclusion in this set without revealing which member you are. That's the cool part of ZK. So zero knowledge proofs are this type of cryptography that essentially allows you to make statements about certain things. Like I can prove that, let's say, I have correctly sent a couple transactions on an L2, and the block with all these transactions is valid, and you can therefore update the state of the rollup, for example. That's how ZK rollups work. In our context, we're proving this set membership inclusion, right? I'm proving that I have a private key to a public key, which is in the verified set of users. The cool part about our specific semaphore instance is that every single user is a user that has been authenticated by a custom hardware device that we manufacture called the orb. So the orb, I can show it right here, is this hardware device. This is a disassembled one. I'm not sure if I have a picture here of an assembled one. Really quickly, these are all like component breakdowns. Maybe this one is good. It's like annotated. You can imagine just like a pretty much a cylindrical ball right? So with the camera, and what this device does is that it's able to tell apart two people from each other, or like it's able to create a unique representation of the randomness of the iris of a human person, and you're able to essentially make sure that every like unique iris code, as we call it, it's an embedding that represents the entropy or the randomness of a person's iris, is unique. The way it does that, if you're interested in how that specific part of the biometrics pipeline works, you can check our documentation. So if you go to whitepaper.worldcoin.org and you check this biometrics section, you can read all about it. Here's just like a cool little diagram that you can see just to understand a little bit how that works really quickly. This one. So essentially, if the person signs up at an orb, and you see that the person has a unique iris code, you're gonna see a very smooth distribution that looks like this one is a non-match distribution. And if the iris code that the person generates is not a unique one, meaning that it's already in the set of verified users, you're going to have a match distribution. So this is how we're able to tell apart essentially whether a user is unique or not without revealing who they are. We don't collect any personal information besides this specific iris code, which is not like personal identifiable information, or PII for short. So essentially every user that has a public key is inserted into this set. The data structure of this set is called a Merkle tree, right? So we have essentially a tree of public keys, and that's how you're able to prove inclusion easily, right? Merkle proofs allow you to prove the inclusion of a set or of an element in a set very easily. And through the use of ZK circuits, we're able to hide which public key is in the set and which private key corresponds to this public key that we're proving. So that's essentially the high-level overview of what World ID is as a protocol. It's this protocol that essentially has this Merkle tree, and it has a Merkle tree root, and the users on their World app are able to have like a private public key pair, and they're able to generate a zero-knowledge inclusion proof against the on-chain tree state. So if a new user gets signed up, they get inserted into the tree once they get verified by the orb, and they can create proofs of inclusion without revealing who they are, completely privately using zero-knowledge proofs. So that's like a high-level overview that I think is important to understand what we're going to go through. I think it's now good if we can start looking at the code. So this is the World ID contracts. So all of our protocol repos are open source. So if you go to Worldcoin or github.com/worldcoin/World ID contracts, you're able to see our contracts. So I'm going to show the World ID Identity Manager, which is the contract that has all the logic for this on-chain Merkle tree with this verifier for verifying inclusion proofs as well. So essentially, there is a structure of a proxy in this tree. So there's two parts. There's a router and the implementation of the identity manager. The reason why we have a router, so if we look at the implementation of the router, is because we have different World ID groups or semaphore groups, meaning that we have separate Merkle trees for different purposes. So we have trees for orb verified users, but we also allow people to verify their phone numbers and their the integrity of their phone device, right? So for example, if somebody downloads the World app as an application verifies the integrity of the device that it's running on, and we can attest through the World app that this person has a functioning phone that is not emulated, etc., etc. So that we also have like separate trees for other signals. And if other people, let's say, build other orbs in the future, or other people build other uniqueness measures, then they're able to add a group to the protocol, and they can route proofs of inclusion against other trees, not just ours. But the tree that is the most important one is the orb verified users tree, which I think is like group number 1 on the production deployment. So that's the reason for why we have a top level router. And if it routes to the, let's say, the orb tree, then it routes to this identity manager implementation. So the World ID Identity Manager is this contract that has essentially all of the logic for the on-chain Merkle tree, how to add members to this Merkle tree, how to delete members from this Merkle tree. If, let's say, somebody loses their world ID, they can delete it and reinsert it. Or if they just want to leave the Merkle tree itself, they can just leave and never re-enter if they want as well. So the way that we have our Merkle tree structured is slightly different than traditional semaphore. So register identities is the function, the most important entry point function to this specific contract. So as the NatSpec docs say, register identities registers identities into the world ID system or Merkle tree. In traditional semaphore, every single insertion, if you want to insert one member, it's one transaction. What we did, since we have a little bit over 3 million users, 3.2 million users into this Merkle tree of verified unique users to the orb, we cannot allow or afford to insert members one by one because that would be all really expensive, and we probably not have enough block space on Optimism to do so. So what we do is we do batch insertions. And the way that batch insertions work is that we have this off-chain Merkle tree, which is in memory in a service called Signup Sequencer, which we'll go in a little bit, which we'll go into in a little bit. Essentially, this service has an in-memory representation of the Merkle tree with all these 3 million leaves or 3 million public keys of these verified users. And whenever a new user gets verified by the orb, this public key gets put into a queue. And once this queue fills up and reaches, let's say, 1,000 new members trying to get into the tree, they get put into a batch. And this batch essentially represents a new insertion. And the way that we update the state of the tree is by creating a zero knowledge proof of the essentially of the change of the tree from the previous tree to the new tree with this new 1,000 identities by proving a new zero knowledge, essentially prove the Merkle tree update in circuit, inside of a zero knowledge circuit. So we prove a batch insertion using these circuits called Semaphore Merkle tree batcher, Semaphore MTB, which is another repo, github.com, Worldcoin, Semaphore MTB. Where we have circuits for both insertion and deletion. They're written using a library called Gnark, written by consensus. It's essentially a Go or a Snark library written in Go, which allows you to create Gross16 proofs. I think they also support other backends for ZK like Plonk, but our circuits are Gross16 over BN254, the BN254 curve, because Ethereum has a given set of precompiles, and the BN254 elliptic curve is one that Ethereum has precompiles for, and it's the cheapest one to do Gross16 proofs over. So we have deletion and insertion circuits, right? So we have a batch insertion. Essentially, this is the structure of the public inputs and private inputs. You have a start index at which you're starting to insert into the Merkle tree. So if we have 3.2 million users, you're going to start inserting at 3.2 million on the start index. The previous root of the Merkle tree, the root after the update, and the identity commitments. The identity commitments are just this array of public keys that we're inserting into the tree. So the array of public keys of the users that are just verified by the orb. And a bunch of Merkle proofs for where they belong in the tree. And the circuit also has a notion of batch size and tree depth. So a batch size, in this case, the ones we run in production are currently, I think, 1,200. We have different batch sizes for different periods of demand, right? So throughout the day, there's a variable number of people signing up throughout the world to an orb. And therefore, if there's less demand, we do smaller batch sizes. If there's more demand, we do bigger batch sizes. And the biggest batch size we have is 1,200. And so if a user gets onboarded, they get put into this queue, as I said, and we are essentially creating a proof of insertion of this batch of users. I'm not going to go too much in depth over the circuits, although if you guys want, I'm happy to go over that as well. But what essentially it's proving is that the Ketchak or the Merkle tree root hash is the Merkle tree root hash of the new tree corresponds to a tree which has the new 1,000 identities that were appended to the tree, which has the previous identities on it. And we create a Gross16 prover over that. And so the world ID contracts, they take in this proof within the register identities method. And if the proof is correct, and it has like the correct public inputs, like the previous root, the starting index, the identity commitments, and the post root, then you're able to insert these elements into the tree, and the Merkle tree root of the on-chain contract gets updated. The cool thing of having an off-chain Merkle tree is that you don't have to essentially do all these Merkle tree operations on-chain, which would be prohibitively expensive. Our Merkle tree is of tree depth 30, meaning that it has 2 to the 30 elements, a little bit over a billion. So currently we're able to support a billion users within the on-chain contracts. We would have to upgrade to a different contract with a different tree depth if we wanted to allow for more. But we think that tree depth 30 is a big enough runway for now.
Do you store that Merkle data publicly available or just internal?
Yes, so that's the cool part of World ID. So the World ID contracts live on Ethereum mainnet, these specific ones, like the ones for doing insertions into the tree. And the reason why we post all of this data to Ethereum is because if you post all of the public keys of the users in the Merkle tree onto Ethereum, anybody is able to reconstruct the tree from on-chain public data, right? You're just able to index all of the events, right? So here in this register identities, there is a event, so tree change from previous to post root, but you're essentially able to parse the call data from every single register identities call. And like, let's say you take a ref or like any archive node that you want, and you take this archive node and you essentially filter every single register identities call, and you're able to parse the call data. If you parse the call data, then you're able to reconstruct the tree construction off-chain from on-chain call data. So if anybody else wants to create sort of a service to create inclusion proofs against this, they're able to do so. Right, so all of the data is public. Like all of the public keys of the users that are verified are public because they're posted on Ethereum.
Cool, that makes sense.
Right, so the register identities function, as I said, like it takes an insertion proof from semaphore MTB, the Merkle tree batcher. And that's sort of like how we do insertions into the tree. We post a proof of the creation of like a new Merkle tree with the new identities added on top of it. And we prove that to the contract. We update the Merkle tree root. And the Merkle tree root is the only public state that you need in order to verify an inclusion proof, which is cool. If the on-chain root is correct, then we're able to essentially prove against that root. And so one feature of this is like, let's say if you are a new user that's verified, you're not able to create an inclusion proof against the Merkle tree unless the Merkle tree root in the on-chain contract has been updated to the latest one, right? So let's say that if I register right now, I'm not able to create a proof against the Merkle tree root until the semaphore MTB service creates a batch proof and it calls the World ID contracts register identities method with the insertion proof. And this also ties into sort of how we do bridging. So essentially, the World app runs on Optimism mainnet. And so all of our users' safes, our users' like World app wallets, are deployed on Optimism. And we also do these Worldcoin token grants every 2 weeks on Monday. And so whenever a user sort of wants to claim a grant, they claim it on Optimism. And the way that they claim it on Optimism is that we bridge the latest roots of the Merkle tree on Ethereum to Optimism using these contracts. I think that's a good tie into this, or a good segue into these
Do you,
contracts. Uh-huh.
yeah, do you mind if I ask something about the registry?
Yeah, yeah,
Um, so it's permission to the, do you mind going back there, sorry?
yeah. World ID contracts, Worldcoin contracts. Mm-hmm.
Cool. So yeah, so it's permission to the identity operator, right?
Yeah,
For like authenticity of
yeah.
the commitments, is that done like you just verify that somebody got their entropy from your from the orb, and then through
Yeah.
that it's fully permissioned until then,
Yes.
or is there some validation?
We curate the tree, right? So we're the only ones who have access to orbs, or the only ones who currently manufacture orbs. and we are the ones who like keep track end to end of the life cycle of a given identity, right? So if a person creates a valid iris code through an orb, and the iris code is unique, we have a backend database of iris codes to public keys, and this iris code database is private, is not public, and the public keys that are inserted into the tree are public. The way that we insert these is like it's a permission identity operator, like relayer. It's essentially an EOA that calls this method from a service called the signup sequencer. I'm happy to walk over that. I was about to get over there in a little bit, but it's essentially a Rust service which has an on-chain Merkle tree, and it's a service that has a server, like a traditional server. I don't know which crate specifically we're using for that, but if I go to server, mod.rs, somewhere here, where am I? Last time I was here. Okay. I'm trying to find something specifically. Anyway, essentially it's a server with like different endpoints, and this server controls an EOA. And whenever there's a tree update, right? So this is like the representation of the tree. It's a Poseidon tree, meaning that each hash within this tree, it's using a Poseidon hash. The reason for why we're using the Poseidon hash function is because it's ZK friendly, right? It's less computationally expensive to constrain or to create a ZK circuit for a Poseidon hash function, because Ketchak is really expensive inside of a ZK circuit for the reasons of like how the Ketchak hash function is constructed. It's really hard to do arithmetic with Ketchak. So yeah, this is essentially the Merkle tree representation. There is the tree version data. Essentially, this service monitors whether the public keys have been inserted onto the tree, and it gets tracked. It has like different versions. There's a database on this service which has the keys that have just been submitted by the orb backend. If the orb backend sends new identities into the signup sequencer, they get put into a queue, right? And so this signup sequencer keeps track of the queue, and once the queue gets filled, it submits a transaction from this EOA. Or first, it calls the semaphore MTB proving system. The semaphore MTB service, that's this Go server, serves back a proof. So there's also a semaphore MTB server right here, right? So this gets called by a signup sequencer, returns a proof for the new public keys that we want to insert, right? Handler, proving system, proof insertion, or proof deletion. We can also delete from the tree with the same way. And once this proof gets back to the signup sequencer, the signup sequencer takes this proof, takes the public input data or like the function call data for this specific register identities method on Ethereum. It creates an Ethereum transaction, submits the Ethereum transaction through a custom relayer. We used to use OpenZeppelin. We replaced it with our custom relayer. And once we send this transaction on chain, the transaction gets verified, like the proof gets verified by the contract. We update the Merkle tree root, and once we emit the event that the tree has been updated, the signup sequencer updates this new tree as finalized. That's like what versioning means, like the tree version data. It just means that it's versioned between like finalized, pending, or just in queue. Like you can see the lifecycle of every public key if the public key is already inserted into a tree, because the signup sequencer also serves Merkle inclusion proofs. Because if you want to serve a Merkle proof for this Merkle tree, you need to have all of the leaves in the actual in memory, right? So that you're able to serve Merkle proofs. And this Merkle proof or this Merkle tree is like, if you think of it, right, like every single public key is 256 bits. There's 3 million public keys, so multiply really quickly, like 3.2 million bytes. It's 102 million bytes. So it's like 100 megabytes or so. So for 3.2 million identities, it's like 102 megabytes that you need to keep in memory, which is way more than any app binary you could have, right? So essentially we don't store the tree on users' apps. So the app backend essentially calls the signup sequencer for a Merkle proof when the user wants to construct a proof of inclusion, right? Like a semaphore proof that, okay, I have a private key to a public key, which is in the verified set of users. So for example, if anyone wants to claim a grant within World ID, like within the World app, so every 2 weeks, like I said, we do these grants distributions. If the users want to claim a grant, they need to construct a inclusion proof that they're a unique person. They verify that inclusion proof on chain, and when they verify that proof, there is a ERC20 transfer from our contracts, from our safes that distribute the Worldcoin token to their addresses. So this is sort of like the life cycle of like the entire thing, from sign up to verifying a proof to like all these sorts of
Cool.
things.
I don't want to go too off track, but I'm also curious. Is there validation of the public keys, or could it be possible to insert one of those in your backend?
Can you repeat the question, or more like go more specific?
So, yeah, so is there validation that public key was generated using an orb, or could it be possible, not that it would happen under normal circumstances, but insert an arbitrary public key into the tree as well?
Yeah, so the public key, but public private key pair gets generated on the app client. So the app itself generates the private public key pair, and the sign up sequencer only learns of the public key once the user has a verified iris code. So the user essentially, when they download the World app, they have this cute little QR code. They show it to the orb, then they stand in front of the orb for a couple seconds. The orb does some processing, generates the iris code, compares it against the iris code backend database. It checks whether the Hamming distance of each iris code is sufficiently distant with the iris code of the user. If the distance is greater than some threshold, then it means that it's unique. If it's unique, they take the public key of the user, which was generated by the client, and it gets essentially put into this queue in signup sequencer. And signup sequencer checks that the backend of the orb said that, okay, this user's iris code is correct, and that this was the public key from the user that was in the app. And once that is checked, then it inserts into the queue, and then you construct the batch, etc., etc., etc.
Okay. Yeah, makes sense.
Yeah, so that's that's sort of like a intro of signup sequencer. I really recommend this. Is like probably the most sophisticated Rust crate that we have. There's a lot of really cool things here, whether it's like end-to-end tests, cool blockchain tests, because there's a lot of moving components. Like we do integration tests across chains with bridging, with ZK proofs, with servers that call other servers, with an SQL database that's local that needs to track and sync and sequence on-chain data, right? So like we have an indexer of on-chain data that syncs with the local SQL database. This is like a lot of really cool things. So if people are interested, I really recommend going through the signup sequencer. Or if you're into ZK, you can also go through our semaphore MTB circuits, which are written in Go. And another cool part is our contractors from Relabs who built a big chunk of these circuits, most of it, also formally verified all of these circuits using Lean. So if you're into formal verification or any formal methods, I really recommend also looking into this, because there's very few people currently like formally verifying ZK circuits at scale and deploying them to production. So this is also like really cool. Like if you're into mathematics and formally specifying like cryptography as formal theorems, then I recommend looking at these libraries. So the libraries that they built work for any GNARC circuit. So if you want to play around with that, I also recommend. Cool. I wanted to get into the state bridge architecture, which I think is also worth mentioning, since I've not seen that many people do stuff like this. It's not hard. It's very simple, trivial things, but there's a few cool things that I think are worth mentioning here. So as I mentioned, we bridge to Optimism because our wallets and our users are on Optimism mainnet. And therefore, we have to bridge the latest Merkle tree route to Optimism in order to verify new users. So to Optimism, we bridge every hour. So when we do an upgrade or an update to the Merkle tree route by the register IDNAs method or the delete IDNAs method, there is this OP state bridge contract, which looks like this. So it's an ownable two-step, meaning that like, okay, if an owner can change things in this contract, but in order to change owners, you need to accept from the other address. Is like a cool thing. I like ownable two-step better than ownable. So essentially, it keeps track of a couple things. It keeps track of the World ID contracts on Optimism. It keeps track of the Optimism bridge. So the Optimism contracts, like for the Optimism L2, there's a couple contracts. One is like the actual L2 contracts where you pose the oracle, like the L2 output oracle, and you have this dispute game, or at least like you have the how do you call it? Like the placeholder. Like you have all the functionality. There's no fraud prover yet live for Optimism mainnet, but like you have all that logic in those contracts. But there's another contract which is called the cross-domain messenger contract. The cross-domain messenger contract is essentially a two-way message passer where you can send messages from Ethereum L1 to Optimism L2 or from Optimism L2 to Ethereum L1. And so this cross-domain messenger address is the address of a contract which is on Ethereum L1, which is able to send messages to Ethereum L2. The way that this message passer works is that the L2 sequencer monitors any changes on this L1 cross-domain messenger contract. And when you send some payload to this L1 contract, it monitors this payload, it takes that payload, and it calls a contract on the L2 through a precompile, which is called the L2 cross-domain messenger, and it calls any target function on the L2 contract with some like arbitrary call data that you send on the L1. So this is how we bridge state from Ethereum L1 to Ethereum L1 to Optimism L2. So essentially, we send messages through this cross-domain messenger, which I'm going to show really quickly.
Is it like who's the message sender? Is it an alias of the L1 address, or is it just the L1 address, or something else?
So cross-domain message sender is a L1 contract written by Optimism. So I can find it really quickly. So if
when it's executed on L2, I'm curious who's the sender.
Ethereum Optimism GitHub. I'm gonna go to their monorepo and really quickly find that contract. Monorepos are nice because at least I've spent enough time in this monorepo, in the Optimism monorepo, that I know where things are. And it's everything in one place: contracts, Bedrock, source, and over here you have L1 and L1 cross message. And okay, there we go. So this contract essentially, and in this contract you have the send message method, and it has a couple parameters. It has two gas. God damn it. Let me just do this so it's more understandable, more legible. So you have address 2, you have UN64 gas limit, a value, and some arbitrary bytes that you want to send. So 2 is the smart contract address to which you want to send a method, or like to which you want to send a message, not method, a message on the L2. So in our case is the OP World ID contract, is the World ID contract deployed on Optimism. Gas limit is the amount of gas that you want to buy on the Optimism L2. So this is cool. What you can do is that Optimism has a separate fee market, right? And gas on Optimism is differently priced than gas on Ethereum. And there's a separate fee market. Like, so Optimism has an EIP 1559 type fee market, same as Ethereum does. And you're able to participate in this gas fee market on Ethereum L1 because the price of the gas on L2 is fed back to L1. So when you want to send a message to L2, you buy gas for the L2 execution on the L1. So you specify what the gas limit of your transaction on the L2 is going to be. And the transaction is going to be differently priced based on this parameter that you specify. Value is just the normal value, right? Like if you want to send some ETH, you can send some ETH through this as well. And usually this is 0, right? Like we're not sending any value. And bytes memory data is the ABI encoded function call. So in our case, I'm going to show it. I'm going to go back to the state bridge. So in our case, there's a propagate root method in here. So this is what we do. We fetch the latest Merkle tree root from the World ID Identity Manager contract that I just showed earlier. So we do World ID Identity Manager at the World ID address. This is just an interface, which has the latest root method. And this returns a UN256, which is the latest root. And this is how we ensure that we always propagate the latest root. and we ABI encode call with the function selector of the receive root method on the OP world ID contract, which is on Optimism. We ABI encode it with the latest root, and this is the bytes memory message that we send to the messenger, or the cross-domain messenger, yeah. And so we instantiate the cross-domain messenger from the cross-domain messenger address. This is an address you can find in the Optimism documentation, or base documentation, or any OP stack network. This is the cool thing. If you take these contracts, you can deploy them on any OP stack network, and it works out of the gate. Like, you don't have to do anything. You just have to make sure that when you use the deployment scripts that we have using Fort scripts, in the environment variable or within the script itself, you just hard code this cross-domain messenger address to the specific one for the given OP stack network that you're bridging to. So you encode, you instantiate this cross-domain messenger, and you call the send message method with the OP world ID address. This is the to field, the message, which is this ABI encoded latest root, and the function selector of the function you want to call on the address you want to call, and the gas limit that you want to buy amount. This is a little bit of like heuristics, like you have to sort of do some benchmarking or some tests using like the gas left opcode. So what you can do is you can do a test where you have a receive root method call with some arbitrary payload, and you just test like how much gas that call consumes, and then you can just either hard code it to whatever that thing is, or you can give it a little bit of a leeway. If let's say that the EVM changes, if let's say that Optimism updates their EVM, and there's some hard fork in the future that changes how some opcodes are priced, then this will break if the gas limit is higher, right? Because if the gas limit is now higher and you set some lower gas limit, this will revert since you've purchased not enough gas limit on L1 to do the transaction on the L2. There's some like finicky things that you need to be aware of. So that's why we just like have this thing as a settable. Like if in any case, like if in any point in time you want to increase this gas limit, there's a setter for this. There's like a set gas limit propagate root method somewhere down here. Set gas limit propagate root by the owner of this contract. So that's essentially why it's not a hard coded like random number for the actual consumption of current of this like current method. In case like you ever change, let's say like Solidity or like the EVM changes how you price things. And that's just a lot of ways to essentially just say that we're sending a message to the L2, and we're essentially sending the latest root to the L2. So the L2 contract called OP World ID, this is not a good contract to show, right? Yes, because inherent polarity bridge, which has the logic. Give me a second. Abstract World ID bridge. Right. So bridge World ID. So this is just an interface, an abstract contract which implements all of the logic of the bridged world ID, and we just make all of our bridged world IDs inherit from this, so that we just make sure that they have the right functionality. So this is essentially the world ID deployed on Optimism, and you have two core methods. One is receive root, and the other one is verify proof. So essentially, receive root is the method that we're going to be calling on the L2, and it takes the existing timestamp or gets the timestamp of the root. If the timestamp of a given root that we're trying to insert, there's a mapping of root history, meaning so if there is ever a root received, it gets appended into this mapping of roots to Boolean or roots to timestamp, sorry. So uint56 to uint56, right? So give me a second. Mapping uint56 to uint128, because timestamps, I guess, or 128. Block.timestamp, I think, is that type. Right. So essentially, it takes the mapping, and for a mapping, as you know, a mapping, if you try to check an entry in a mapping, it's 0 by default, right? So if it's not 0, it means that somebody already sent a root, because the timestamp otherwise would have been non-zero. Otherwise would have been 0. So if it's not 0, it means that we cannot overwrite the root. We already had sent the root before because it had an associated timestamp. So if we've already propagated that root, that means that we cannot like reinsert a root into validity again. So yeah, we take the current timestamp and we upgrade or update the latest root on Optimism to the one that we're sending from Ethereum, and we just set the history on the timestamp into the mapping to the current timestamp, and we emit an event. And this event is also important for us because the signup sequencer listens to this event, and so that it like checks that this root is finalized. And it sings the DB and says, okay, this version, this tree, Merkle tree, is already part of the finalized one. So if someone is sending me a request for a Merkle proof, I can tell them, hey, okay, I've already seen this root finalized on Optimism. We can serve a Merkle proof for this, and here you go. So that's sort of why this event is also here, besides just observability for anybody else. I think something that's cool to mention is that a lot of protocols don't really have sophisticated monitoring, alerting, and data pipelines. We have a fairly sophisticated one. We have essentially these like on-chain events that we emit, and we feed all of these events through indexers to Datadog, and Datadog is this essentially like data platform that allows you to create different dashboards, etc., etc., etc. And using different Rust crates like tracing, logging, and other ones, you're able to essentially give these data feeds to this like data dashboard. You're able to track it really efficiently, and then you're able to have better incident responses. So for example, if like a root failed to be bridged for whatever reason, we see that, right? And you can see dashboards, how many routes have been failed, how many proofs have failed, et cetera, et cetera, et cetera. And you can like try and see why. So if there's like a function call that reverts, you can just see automatically the transaction hash. You can feed it into Tenderly, you can debug or whatever. And if there's something critically breaking, let's say that the signup sequencer is down and now people cannot serve inclusion proofs, et cetera, et cetera. We also have a pipeline through like Ops Genie for like paging people to like fix the service or like redeploy something. And our services like run on AWS, like all these servers, right? Like the signup sequencer, Semaphore MTB, et cetera, et cetera. So I feel like a lot of these like blockchain protocols could like use a lot of these sorts of things. There's a few people building startups so that you improve monitoring in the current state of things, because it's not easy to do these things at scale in a team. Because usually when you have a protocol engineer, okay, they're already busy learning DVM, Ethereum, how to build, let's say, a DeFi primitive, like depending like on what type of engineer you have, it's really hard to build like be a solid or really good Solidity engineer, and at the same time know Rust and know how to do monitoring and tracing and infrastructure and provisioning and all these sorts of things. There's just a lot of complexity. So something I really want to see in this space is like better ways of doing this at scale, in a way that's more legible and easy to use for the average protocol engineer. We need to have like there's a couple startups. Like one of my favorites is Phylax, is done by a friend of mine called Odysseus. You're essentially, it's like a forged script where you're able to like create a Foundry opcode to like do tracing and monitoring in real time just using Solidity. Similar like Foundry, right? Like Foundry allows you to do tests in Solidity. You no longer have to write like broken JavaScript and switch context. So it's the same thing for tracing. I just wanted to mention that because I think it's cool. Yeah. Okay. What do you guys want me to talk about? I can go into
Yeah,
a
I was
lot of.
just curious if we could look quickly on the validation
Mhm.
of that new route on Optimism. Like, how are you validating it?
Yeah. So this is a little bit of a permission. Okay, this is a cool mechanism that I had to write actually. So the way that it works is that this propagate root method is external and can only be this can be called by anyone, right? So this propagate root method can be called by anyone. Anyone can call propagate root, and they can propagate the root more often if they want to. Like if let's say there's an app developer on Optimism and they need the roots propagated more frequently than we do by default, they can propagate it themselves. And same if like anybody else wants to build another bridge to a different network, we're also issuing grants from the Worldcoin Foundation. I'm just gonna mention that really quickly. So I'm personally part of the Worldcoin Foundation. I'm not part of TFH. we have this grants program. And one of the grants types that we do is bridges to EVM and non-EVM chains. So if you implement your own bridge, you can apply for a grant, yada, yada. I really recommend this website, worldcoin.org/RFP. So yeah, back to what I was saying. So this propagate root method can be called by whomever, how many times they want. The cool thing is on the other side, how do you validate that the roots that are propagated are the correct ones? So this received root method is only owner, but who is the owner here? The owner is an EOA or a contract on the L1. In this case, the contract on the L1 that owns this contract on the L2 is the OP state bridge. How do you make a contract on the L2 ownable by a contract on the L1? Well, there's this cool mechanism that I had to build, which is called this cross-domain ownable contract. So there's there's three different types of cross-domain ownable. Optimism built the first two, and I had to build the third one, which had the properties I needed. So let me just quickly show this one, cross-domain ownable 3. And funny enough, the PR that I opened for this was number 4844, like the EIP. It was hilarious. Yeah, so cross-domain ownable 3. So this essentially is a wrapper on top of the ownable contract from OpenZeppelin. And it has this toggleable variable, Boolean variable, which is true or false, which it is local, which means if is local is equal to true, ownable behaves like regular ownable. It's like a local ownable on the same blockchain. But if is local is set to false, it toggles to the cross-domain messenger, or it uses the cross-domain messenger to check for the owner, the message sender. Sorry, for the message sender, it checks the cross-domain messenger. So I'm going to show you the check owner method, which implements this. So if it's local, it behaves like a regular ownable contract. Owner, message sender. If it's not, then revert with caller is not the owner. If, however, is local is equal to false, then you instantiate the L2 cross-domain messenger. There is a pre-deploy contract. I think Optimism has like a prefix for precompiles, so you can really easily spot precompiles on Optimism. It's a precompiled address, like smart contract with some functionality. And I think this one is like 420000, and it ends with a 7 for the cross-domain messenger on the L2 side. And this contract is the one that is the message sender for anything that was sent from the L1, right? So if I call receive root on the OP World ID contract from the L1 through the OP state bridge, the message sender is going to be this contract with the payload from whatever I sent from the L1. And the sequencer of the L2 is the one that is responsible for calling things through this precompile. So this, what it does, is it checks whether the message sender is the messenger, right? So it checks that the person that's sending, or the contract that is sending this call is the precompile that like sends messages from L1 to L2. And it checks that the messenger's cross-domain message sender is the owner, right? So this little field is the contract or EOA that calls the L1 cross-domain messenger, which was the OP state bridge, right? So now we're able to make the OP state bridge the owner, right? So we're essentially able to check that the owner of the L2 contract is whomever was the cross-domain message sender of the messenger call. I think this is a really cool mechanism. Did you guys get that? Or should I repeat?
Yeah. So the L2 cross-domain messenger, that is like the OP contract, the precompile, right?
Yeah.
So when you call that cross-domain message sender, how does that differ per caller? Because messenger is just a contract, right?
Yeah. So the messenger, when you instantiate it, this gets set to whatever the cross-domain message sender is for a given call.
Oh, okay. Interesting.
Right. So because look, like when you're doing a transaction here, the address message, like you're checking that the message sender, right, like the person who initiates the call of the contract, is the messenger. And in this call, the messenger, in its like internal state of the contract of the L2 cross-domain messenger, it sets the sequencer is monitoring this. So the sequencer sets this through a privilege like EOA, or I don't know the specifics, but it has a way to
Right.
set the cross-domain message sender, and it sets it to whomever who called the L1 message sender, right? So it just puts
Okay.
that as the cross-domain message sender, and that's why it's able to tell that the cross-domain message sender was a given EOA or L1 contract that called the L1 cross-domain message sender. So this is sort of like
I see.
how we're able to check cross-domain ownability, and this is how you're able to sort of permission this in a way that's not centralized. Like we're not just having
Right.
a relayer that is only owner, and we're just telling you these are the latest routes. No, you have the end-to-end correctness or assertion that you're never be able to bridge anything that was not the latest route on the World ID Identity Manager on the L1. You can only bridge that latest route. You're not
Right.
able to bridge anything else, and anybody else can call it. Like if you want to bridge routes as often as you want, you can do that. One better improvement that we're exploring right now through Worldcoin Foundation grants is the usage of storage proofs. Storage proofs are this concept that essentially allows you to prove that some storage slot on Ethereum, on some like node, let's say Geth, like on the EVM on Geth, has some storage slot for some contract. You're able to create a zero knowledge proof of the Merkle inclusion proof of some storage slot in the Ethereum state Merkle tree. So that was a bit of a handful, right? So like if
So
you have
yeah.
Ethereum state, right? I'm just gonna say it one more time. So Ethereum state is a Merkle tree. All of Ethereum state is a Merkle tree with all of the data of Ethereum. The reason for that is that you can get Merkle proofs of some state being included. So if let's say you run an Ethereum full node or archive node, you're able to prove that any state is part of Ethereum canonical state. And storage proofs allow you to create a zero knowledge proof that some state is indeed included on Ethereum, and then you're able to succinctly verify that proof. You don't even have to run the Merkle proof service, or you don't have to run a full node. You're just able to verify a you're able to verify a zero knowledge proof, and then you know that some state was included on Ethereum. So this is sort of like the usage of storage proofs. And since Ethereum and L2s, L2s have direct access to Ethereum state, so they're able to verify the latest Merkle tree root of the Ethereum state. You're able to permissionlessly, with no added trust assumptions besides the ZK security guarantees, you're able to permissionlessly bridge state from L1 to L2 and
Right.
vice versa.
So something like Axiom. I was initially going to say with the light client, but you don't need the light client because you have storage access.
Yeah.
Okay.
Axiom, Gratis, Lagrange, these three startups, as far as I know, are the main ones building storage proof solutions. And this is essentially what they're doing, right? Like they're proving inclusion of some state on Ethereum, on the Ethereum Merkle tree. And you're able
That's
to
cool.
consume that either on other contracts on Ethereum or on the L2. And the cool part of this, what they do also is like you're able to do statements or attestations, as people call them, with this state. Like you're able to prove that some state was on Ethereum, and then you're able to feed that state into a circuit, and you're able to do arbitrary transformations on it. Right? You're able to do, let's say, like a ZK EVM. You write a Solidity contract, you take some state. You have the entire trace from the Ethereum state to some output, and you're able to prove that that original data that was fed into the ZK proof came from Ethereum. It's just mind-blowing stuff that you can do nowadays.
Yeah. No, that's really cool. This might be going a little bit off track, but how do you access that L1 storage on L2 or like with OP?
So L2s, by definition, are L1 smart contracts, right? So you have direct
Right.
access to Ethereum state. Like you have access to the latest Merkle tree root of L1, like Ethereum L1. So you don't have to have any
Okay.
assumptions. Yeah.
Yeah, that makes sense.
Cool. So yeah. What can I talk about next? We have. I'm happy to go over. I don't have.
Yeah, no hard stops either. Maybe one last question, DC, if you can scroll down one last time about just to make sure that I understand this correctly.
The
So every
cross-domain,
time there is a transaction, sorry?
the cross-domain ownable thing you mean?
Yeah. If you can scroll down. Okay, so yeah, just to make sure I understand this correctly. So every time there is an L1, L2 transaction, this X domain message sender is basically set.
Yes. Yes, this
Okay.
L2 cross-domain message sender or messenger is a precompile. Like Optimism has this library called predeploys, and it just has the hard-coded addresses of the precompile. So on any OP stack network, this predeploys will be automatically populated with the contract addresses for all of the precompiles. And since all OP stack networks are the same from the EVM perspective, the addresses will be always the same for the precompile. Because a precompile, by definition, you have complete control over. Like precompiles are just addresses, same as on Ethereum, right? Where you just call them and they, as a precompile, they have a native compiled program that is not EVM, it's outside of the EVM, and it's just like gives you the output for whatever you feed it, right? So on Ethereum, you have a contract for Ketchag or for like Ecad, Egmol, like different precompiles on Ethereum that do stuff for you, like different hash functions, different things. And on L2, you have complete control over this, right? So it just calls this precompile contract, and the precompile contract is called by the sequencer with the payload that you send to the L1 cross-domain messenger from whatever place that you send it from, right? So this L2 cross-domain messenger is this precompile that essentially calls the contract on L2 with the payload that you set. So if I go back to this send message method, so this is the payload that you have. It essentially says whom you want to send the payload to, how much gas you want to buy on the L2, the value that you want to attach to the call, and whatever the ABI encoded data you want to send. So in our case, we're ABI encoding, let me go back to OP State Bridge. We're ABI encoding the propagate root method, which essentially ABI encodes the receive root method as the selector, the function selector of the OP World ID contract with the latest root. It ABI encodes this, so you have some bytes memory, and these are the bytes. These are the bytes that you send to L2. So the L2 receives a call from the precompile with this bytes memory. And what it does is that the OP World ID contract, you hit the call, the contract will check, the EVM will check what selector in this contract it is. It will match this selector, right? Like the 4 bytes of the hash of receive root uint56, right? Boom. And it will match this selector. It will call this within your root, and it will check that the message sender was the precompile, and that the cross-domain message sender, right? It'll check that the message sender is the precompile, and that the cross-domain message sender is the OP state bridge contract, which is it's this one, right? So this is the owner in effect. This is the owner of the OP World ID contract, and that's how you're able to semi-permissionlessly bridge state. Like you still have an owner here, because like this is the owner of the thing. So if this gets upgraded to some other owner, and that other owner is feeding it bogus data, then it's bogus data that you're feeding it, and you can like fool it, and you just break the security assumption. So this is secure as long as the owner of the OP World ID contract is something that is feeding it the actual latest root of the World ID identity manager. So yeah, it's semi-permission in the sense that you're able to have provenance, but currently we don't have storage proofs. And in the future, this can be sorry. In the future, this can be completely permissionless using storage proofs, because L2s have direct access to Ethereum state, and they're able to validate storage proofs with no added trust assumptions besides the security assumptions of the actual ZK storage proof, right? Like if there is some error in the cryptography of how you implement the circuit, maybe you under constrain it and you're able to feed it incorrect data, and you're able to verify a valid proof even though you have an incorrect proof on functions or an incorrect witness, then you're able to game it. But then that's just a security assumption of the implementation. If you assume under a security model that it's correct on your formula verifier or whatever, then you're able to have a really high assurance that it's completely permissionless. Like you're able to verify a storage proof on the L1, on the L2, and you're able to permissionlessly bridge state. And the end vision, something I can mention is like how people are thinking about like interoperability in the future. Any ZK rollup, as long as you update the state of the ZK rollup to the L1, you post like the latest update, you prove the state transition, etc. you're able to permissionlessly bridge assets from any homogeneous zk rollup to any other homogeneous zk rollup. So let's say if you have a Polygon CDK chain, like their own like rollup framework thing, or similar to OP Stack. OP Stack is optimistic. Polygon CDK is zk, right? So if you have a zk rollup that is homogeneous, you're able to trustlessly bridge assets from one to another because you're proving a zk storage proof. Sorry, you're proving a zk storage proof that like some asset was burned on Polygon CDK chain 1, and you can mint it on Polygon CDK chain 2 with no, like you're essentially breaking this like fragmentation problem because you're able to permissionlessly bridge assets through storage proofs. That's like sort of like how people are thinking about interoperability nowadays. There's some other constructions, but this isn't.
Interesting.
Yeah, there's honestly like I can go into 100 different directions. There's just so many cool things in this space. I don't have enough time to keep up with everything. I recently transitioned to the Worldcoin Foundation just so that I can spend more time on just this, like cool cryptography research. I'm currently learning ZK myself and like the math. Like I'm learning abstract algebra. I'm learning like proper cryptography and ZK stuff. There's lots of cool resources. We can do an entire like another hour podcast just talking about that. But essentially, like the reason why I'm at the foundation now is because I can work with different teams in the space, like top teams in the space that apply for grants, and we can also do partnerships of different sorts to work on cool research problems on our end. Or also, since WorldCoin is literally like building tooling for the world, essentially like everything that we build and help other people build as a team, like if we contribute upstream to Ethereum or to OP Stack or to anything else, there's like a lot of freedom for me to like work on different things. And that's sort of like why I chose this, right? Like I'm able to now work on like Ethereum core if I want to, if it's like important, right? Like if there's like EIP 4844. Worldcoin, for example, was an important contributor to EIP 4844. We built the KZG ceremony coordinator. So like this server that everyone, like, I don't know if you guys went to ever to ceremony.ethereum.org to participate in the KZG ceremony. But the server that was running and doing like coordinating all these things was built by us. So yeah, that's like some cool stuff that we worked on.
Are you planning on moving the identity commitments to data blobs or
Huh?
keep it in call data?
Sorry?
Are you planning to move the identity commitments to data blobs at all, or are you just going to keep it in call data?
Cool question. You need to keep them permanently. Like blobs are
Yeah.
like shortly lived. Like they only live for 18 days or so. So it's enough
Yeah.
for so essentially how this works is that the L2 here, the L2 nodes are responsible for keeping the data available in perpetuity. So if you ever want to retrieve all of the call data of all the L2, you need to query the L2 archive node, right? It's no longer going to be a task of the L1 because all of the L2 is going to be posting data to blobs, and blobs are going to vanish into like into the ether, as they say, right? And after 18 days, like that data is no longer going to be retrievable. You only are able to retrieve it from the L2 state. And the way that this is bypassed is that 18 days is enough for a ZK proof to be posted and for the state root to be updated, and or for the dispute game, like the fault proof challenge game, where you like have a party that like challenges a state transition. You run a virtual machine inside of the EVM, and the virtual machine runs the EVM. Is like a very very weird thing. Like you should definitely have some guys from Optimism explain the fault proof contracts, like Vex or somebody like that, because it's like when they did the explanation for me, it was kind of crazy. It's a bit hard to follow, but it's really interesting. But yeah, off topic.
Yeah, for sure.
Yeah, we're not going to be posting to blobs. We're going to be only posting to call data on Ethereum, but
Yeah, I think
we're
that makes sense.
benefiting from blobs because we run on Optimism mainnet, right? And therefore, if Optimism mainnet posts their data to blob space, it upstream benefits us because we have cheaper execution and call data on the L2. One last actually cool thing that I can mention on the ZK side, since cold data is the most expensive thing on the L2 side, you're able to, whenever you have the opportunity to move cold data into execution, you should do that. Because execution is extremely cheap on the L2 compared to cold data. Since L2 cold data becomes L1 cold data, then you really have to be really considerate with what data you choose to put as cold data on the L2. So here, OP World ID has this verify proof thing. Okay, it's in the World ID bridge contract really quickly. So the verify proof method, this is the semaphore inclusion proof, a verifier for the semaphore protocol, right? And this is all the code that I need to pass. The public inputs, you're gonna have to pass either way. There's no way that you're gonna go around this. You need to pass the public inputs. But the proof, however, the proof, you only need to pass, well, the proof you need to pass in its entirety as call data to verify proof, but the semaphore verifier itself can take only 4 instead. This is a cool property of like ZK circuits, but essentially Gross16 proofs are 4 points on an elliptic curve. And each point is XY coordinates, right? Like, so it's eight numbers, like XY, 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 right? And each number is 256 bits. And what you can do is if you have just the X coordinates of the 4 points on the elliptic curve, you're able to reconstruct the Y points by just checking the curve. Like, oh, for this X, what is the Y for this X? You can just reconstruct that because you already know what the curve is, and you're able to like reconstruct the second coordinate from it. So if you're able to just pass 4 points, 4 coordinates of each individual point, like 1 coordinate of each individual point, you're able to reconstruct the other ones as execution, and this saves a ton of gas on the L2. There's this blog post by Remco, which is one of my teammates on the foundation, and he's like the galaxy brain behind all of the ZK stuff that we do, and protocol stuff that we do. So this is essentially like a write-up that tells you like how to reconstruct the second point in the field that you're working on, and essentially how compression works, how decompression works, and essentially the implementation of the verifier that we built. So all of our ZK verifiers, our Gross16 verifiers, are optimized for like minimizing call data, and you reconstruct everything that you would have to pass as call data within the actual execution, which like makes our Gross16 proofs very cheap. And this is important because we're by far the biggest constructors of snarks on Ethereum. Like we're 90% of all snarks ever created. Like if you think of all the rollups, all of the other like ZK privacy, whatever, we're like 95% of the snarks and starks, or like not, sorry, like 90%-ish. And it's getting small, like bigger and bigger. Like we're by far the biggest producers of proofs. So we spend like millions of dollars literally on proofs and verifying proofs on Ethereum. So anything that can shave off like a cent is useful for us. So this is why we do like these hardcore optimizations of ZK verifiers and stuff.
How frequently do you do batches? Do you just do them once they fill up, or?
So yeah, so it's the biggest batch is 1200, as I mentioned earlier, and we do them every hour. So the latency that we have is like every hour we do a batch, or if it's full, like if it's 1200, like every 10 minutes, we do 1200 every 10 minutes because we need to like process the queue. If an hour hits and there is less than 1200 and there's less than the other verifiers that we have, we do smaller batches. So let's say that an hour goes by and there's only 500 people in the queue. Well, we do a batch of 600, which is the second biggest batch that we do have. So in the World ID contracts, there's a mapping of verifiers that I can show you really quickly. Batch insertion verifiers. So it's a verifier lookup table. And what the lookup table does is you call this lookup table with the number of insertions you want to do. And we support, I think, I did the trusted setup for all of these. So each circuit, like each semaphore MTB circuit, is a different R1CS circuit depending on the batch size that you have, since it's a parameter to the circuit and you have to constrain every single identity that you insert. We support different batch sizes, and you have to do a separate trusted setup. So I can also show that very quickly. SMTB ceremony. So this repo has all of the details for how we did our trusted setup. And I built a lot of the tooling in Go for doing the trusted setup for our circuits. So this is like the guide for how you do it. And these are the batches we support, 10, 100, 600, and 1200 for insertion. And there's another separate circuit for deletion. And we support batches of 10 and 100 for deletion. And this is like the entire procedure. So if you want to go to github.com/worldcoin/smtb-ceremony, and the guide MD file in here is like the entire procedure of how to run our trusted setup, and you can also verify it. So if you go to the production contracts, like if you go to our documentation, you're able to find the production contracts. You're able to verify that the trusted setup is, or like the verifiers were generated through a public trusted setup that we did. You're able to like reconstruct the verifier and check that the verifier contracts match, which is something that very few people, I think, have gone through the length of, especially like ZK people. Like L2Beat is doing a great job with this, like trying to verify all these things. I had Bartek from L2Beat verify this once for our previous circuits. We already updated them, but it's cool that you can verify it, right? Like here you have the transcript of all the contributors. We only had 14 or like some 20 something, 16 contributors. The reason for that is that our files are gigantic for the circuits. And this is just for inserting into a Merkle tree that we curate ourselves anyway. So it's not like a, let's say like a tornado cash ceremony where you're dealing with funds. Here, like the worst case scenario is that if all of these participants in the ceremony, some of them being members from TFH and or Worldcoin Foundation, or members from like the ZK community and others, were to collude, the assumption of the trusted setup is that if one of N is honest, then the entire ceremony is honest, meaning that all of the contributors need to be dishonest for the trusted setup to be compromised. And if that were to happen, the worst thing we can do is that we can create incorrect Merkle tree roots, and you'd be able to like create proofs against incorrect Merkle tree roots of a tree we curate ourselves through the orb and etc. So worst case scenario is like, okay, not too bad, and it's a one of n assumption, which is very good. Is much better than if all members had to be honest, or let's say like a 20% or 30% had to be honest, like for like some consensus protocols like Ethereum, like you need to have 33% of the validators to be up and honest for
Nice. DC, this was really great. A lot of stuff that I definitely need to go through because, yeah, this was a lot. If you can send me all the links that you think
all
would
the
be necessary, and put them in the description below.
Mhm.
Obviously, the GitHub, your Twitter, Worldcoin documentation.
Yes.
Owen, thank you very much for co-hosting, man. For the interesting
Yeah, thank
question.
you. No, this is really fun.
DC, thank you for taking the time, man. This was super
Awesome.
interesting, man.
A pleasure. I'm happy
Awesome.
to go.
Definitely. So there's gonna be a DC part 2 episode in the future for sure.
Cool.
Okay, guys, then thank you very much and see you in the next one.
Awesome.
Bye-bye.
Have a good one. Bye-bye.
Yeah.